This video is brought to you by Skillshare. Use the link in the description to receive a free 1-month trial and learn something new today with access to more than 25,000 online classes. Top Thrill Dragster is one of the few roller coasters in the theme park world that requires no introduction. Although this thrill machine was constructed more than 15 years ago, it has managed to stand the test of time, and it remains as one of the top-ranked roller coasters in the world today. When Dragster opened to the public in May of 2003, it offered an experience that was unmatched by any other coaster, launching guests from 0 to 193 kilometers per hour in just 3.8 seconds, and catapulting them 128 meters into the air at a 90-degree angle over the massive top hat element. At the time of opening, it was not only the tallest and fastest roller coaster on Earth, but it was also the world's very first Stratocoaster, an exclusive title reserved only for closed-circuit roller coasters exceeding 122 meters in height. Even today, Top Thrill Dragster is one of only 2 Stratocoasters in existence, the second one being Kingda Ka at Six Flags Great Adventure, which opened in May of 2005. Top Thrill Dragster and Kingda Ka were both built by Intamin Amusement Rides in collaboration with Werner Stingel, and they are both variations of Intamin's hydraulically launched roller coaster model known as the Accelerator Coaster. The first Accelerator Coaster was aptly named Accelerator, and it opened at Knott's Berry Farm in June of 2002, setting the groundwork for the taller and faster coasters that would come later. Although this video will focus on the engineering behind Top Thrill Dragster specifically, most of the information will also apply to the other Intamin Accelerator coasters, like Kingda Ka and Accelerator, however the exact figures may vary from ride to ride depending on their size. So now that the introduction is out of the way, let's jump right into the mechanics of Dragster. Once the train is loaded with passengers and it is ready to be launched, it is propelled forward to the beginning of the launch track by rubber drive tires that are powered by electric motors. The catch car is then positioned underneath the train by a steel cable system that we will discuss in more detail shortly. The catch car is a long piece of steel that rides in a trough down the middle of the launch track, and it connects to the underside of the third car of the train. There is a V-shaped groove in the top of the catch car, which connects with a metal pin known as a launch dog that is dropped down from the bottom of the car. The launch dog is normally held in place by 2 permanent magnets. However, when the train is positioned in the launch area, an electrical contact is made between the train and the track, which allows current to flow through wire coils that are wrapped around the magnets. This generates a temporary magnetic field that opposes the permanent magnetic field from the magnets, thus allowing the launch dog to drop down onto the catch car. After the launch dog is dropped down, the rubber drive tires are retracted, and since the launch track is sloped upwards at a slight angle, the train then rolls backwards and the launch dog slides into the groove in the catch car. When the train is launched, the force between the train and the catch car holds the launch dog in place, and when the catch car reaches the end of the launch track, the train simply overruns the catch car, and the V-shaped groove pushes the launch dog back into place where it is once again held by the permanent magnets. It is extremely important that the launch dog retracts, because there's always a possibility that the train will not clear the top hat element, and it could fall back towards the launch track at nearly 200 kilometers per hour in what's known as a rollback. If the train were to reconnect with the catch car at that speed, the result would likely be quite destructive. After the train overruns the catch car and heads up the tower, the catch car is slowed down using eddy current brakes, and it is returned to the beginning of the launch track by the steel cable system for the next train. The steel cable system consists of 3 separate cables, which connect the catch car to a large rotating drum that is powered by the hydraulic launch system. 2 launch cables are connected to the front of the catch car, and they run in grooves down the length of the launch track. At the end of the launch track, 2 sets of pulleys guide the cables into the hydraulics building, where each cable wraps around one end of the drum. A retractor cable is connected to the back of the catch car, and it wraps around a pulley at the beginning of the launch track before running along the bottom of the track to the hydraulics building. The retractor cable wraps around the center of the drum, and it is wound in the opposite direction to the launch cables. When the drum spins clockwise in the orientation shown, the launch cables are wound onto the drum, which pulls the catch car to the right, while the retractor cable is unwound from the bottom of the drum. Conversely, when the drum spins counterclockwise, the retractor cable is wound back onto the drum, which pulls the catch car back to the left, while the launch cables are unwound from the top of the drum. Every time a train is launched, the 2 launch cables are put under a great amount of tension, which causes the cables to stretch under the load. In order to keep the cable system taut, the pulley at the beginning of the launch track is equipped with a tension regulator to pick up the added slack in the retractor cable. The pulley is housed inside the launch track, and it is positioned on a horizontal track of its own, which allows it to move back and forth as the cables change length. The tension regulator connects the pulley to the launch track, and I'm fairly certain that it simply uses a preloaded spring to apply force onto the pulley in order to maintain a minimum tension in the retractor cable. The force on the pulley does not need to be that high since the retractor cable is not directly loaded during a launch, but the cable does need to remain taut so that it does not slip off of the pulley. On the other hand, the amount of force that is needed to launch one of Dragster's trains is huge, and we can estimate this force using Newton's second law by multiplying the average mass of a train with its acceleration. According to the park, an empty Top Thrill Dragster train has a mass of about 15 tons or 13,600 kilograms. Each train can carry 18 passengers, and the average mass of an American adult is 82 kilograms, so we can approximate the total mass of the passengers as 1,500 kilograms. This gives an average total mass of about 15,100 kilograms for a fully loaded train. The ride accelerates the trains from 0 to 53.6 meters per second in 3.8 seconds, which corresponds to an acceleration of 14.1 meters per second squared, or about 1.4 Gs. Using these figures, the average force required to launch a train can be calculated as approximately 213 kilonewtons, or 48,000 pounds. Since there are 2 launch cables pulling the train, the force in each cable will be half of this value. In reality, the actual force would also be slightly higher because the hydraulic launch system needs to overcome friction and drag. In addition to force, we can also estimate the average amount of power that the hydraulic system needs to provide in order to launch a train. At top speed, the kinetic energy possessed by a train can be calculated as half of its mass multiplied with its velocity squared. Using the velocity and average mass of a fully loaded train from before, this gives about 21.7 megajoules of energy. I also did some back-of-the-envelope calculations to estimate that an additional 3.1 megajoules of energy needs to be provided to overcome friction and drag during a launch. This means that on average, the hydraulic system needs to provide about 24.8 megajoules of energy in just 3.8 seconds. These figures correspond to a power output of about 6.7 megawatts, or just under 9,000 horsepower, which is actually comparable to the power output of a real Top Thrill dragster. The technicians who work on the ride estimate that the hydraulic system is capable of generating between 10,000 and 15,000 horsepower at its peak output, however I was not able to confirm an exact value. The exact amount of power provided by the hydraulic system varies between each launch, and it depends on the mass of the passengers, as well as environmental conditions such as humidity, atmospheric pressure, and temperature, which affect friction and drag. Before launching a train, the ride computer uses data from the previous 3 launches to estimate how much power it needs to provide. Sensors along the track are used to measure the speed of each train, and if the trains are running slower than expected, then the hydraulic system will provide additional power for the next launch. Conversely, if the trains are running faster than expected, then the hydraulic system will provide less power. This is the reason why a sudden change in the weather can cause a train to stall on the top head element and roll back down the tower. The massive hydraulic system itself is housed inside a masonry building that is located at the end of the launch track. The large rotating drum that we saw earlier is located at the center, and 16 red hydraulic gear motors are positioned around the circumference on each side for a total of 32 motors. On each side, the 16 motors connect to a massive steel gearbox, which transfers power from the individual motors to a single output shaft. I have seen a few sources claiming that this is a planetary gearbox, however I was able to reach out to the company that manufactured it, and they confirmed that this is not actually the case. Inside the gearbox, each hydraulic motor connects to one of 16 helical pinion gears that are arranged in a circular fashion around a central bull gear. These pinions work together to spin the bull gear, which is connected to a large hollow output shaft. Although this arrangement looks similar to a planetary gear set, it is fundamentally different because there is no ring gear around the outside. The output shaft from each of the 2 gearboxes is connected to the 2-meter diameter cable drum, and at top speed, this drum spins at approximately 540 RPM. That's equivalent to 9 full rotations per second. To accomplish this, each of the red hydraulic gear motors uses 2 internal gears to convert the flow of high-pressure hydraulic fluid to rotational motion. As fluid passes through one of the motors, it is forced to flow around the outside of 2 gears, which causes them to rotate. One of the gears drives the output shaft of the motor, which is connected to one of Dragster's 2 gearboxes. The hydraulic system that supplies the high-pressure hydraulic fluid to power the motors is comprised of 4 identical subsystems, each powering 8 of the 32 motors. To make things a little easier to follow here, let's isolate one of the subsystems to see how it works on its own. At the core of the system is a hydraulic piston accumulator, which is used to store hydraulic fluid under high pressure. The accumulator is divided into 2 chambers that are separated by a floating piston, and one of the chambers is filled with nitrogen gas. This nitrogen chamber is connected to additional backup bottles that allow the system to use a greater volume of gas. Hydraulic fluid is pumped into the second chamber by a 500 horsepower hydraulic pump, which compresses the piston and pressurizes the gas. The hydraulic fluid is practically incompressible, and the pressure inside the accumulator is dependent on the volume of gas displaced by the fluid. Prior to a launch, the accumulator is pressurized to about 32 megapascals or 4,600 psi, and this process takes about 45 seconds. When the ride operator hits the launch button, the cartridge valves at the end of the accumulator are opened, and the pressurized hydraulic fluid is delivered to the motors which spin the drum, reeling in about 100 meters of cable in just 3.8 seconds. As the hydraulic fluid passes through the motors, it is collected in a large reservoir to be used again for the next launch, and the whole process starts again. The exact same process also takes place in the other 3 hydraulic subsystems simultaneously, and they have to work together in perfect unison to power the ride. While the accumulators are recharging in between launches, an auxiliary motor is used to spin the drum in the opposite direction, which unwinds the launch cables and returns the catch car to the beginning of the launch track. In total, the entire system contains about 15,000 liters or 4,000 gallons of hydraulic fluid, and it is designed to launch a train about every 60 seconds. Now, of course, if a train is going to be launched 128 meters into the air at 193 kilometers per hour, then there also needs to be a way to slow the train down, and this is accomplished with eddy current brakes. The brake run at the end of the ride has fixed metal fins that protrude up from the track, and these align with permanent magnets that are mounted on the bottom of the trains. The fins are conductive but non-magnetic, and as the train passes over them, the magnetic field from the permanent magnets induces circular electric currents called eddy currents. These electric currents create a magnetic field of their own, which opposes the magnetic field from the permanent magnets. This generates a drag force that acts on the moving train opposite to its direction of travel, and the magnitude of this force is proportional to the train's velocity. Once the train is slowed down, rubber drive tires are used to bring it to a stop before moving it into the station. In order to handle rollbacks, when a train does not clear the tower, Dragster's launch track is equipped with a braking system of its own that functions in the same way as the final brake run. However, the metal fins on the launch track can be moved up and down using pneumatic cylinders so that they do not generate a braking force while a train is being launched. The springs inside the cylinders hold the brake fins above the track, and just before a train is launched, the cylinders are pressurized, which compresses the springs and lowers the fins. As the train speeds down the track, proximity sensors are triggered which tell the pneumatic cylinders to depressurize so that the fins are raised back to their default position. The spring-loaded mechanism inside the cylinders ensures that the braking system is fail-safe because the brake fins will rise automatically in the event of a power failure. The ride also uses more brake fins than are necessary to stop the trains, and the computer will not allow a train to be launched if any of the sensors are not working properly. In total, there are about 400 moving brake fins along the launch track, and the ride uses more than 800 sensors. The experience on Top Thrill Dragster may only last 17 seconds, but it takes many complex systems all working together to make it happen safely and reliably. From the towering steel structure all the way to the powerful launch system, you really have to admire just how much engineering went into this ride. Of course, whether you choose to do that from the ground or from 128 meters above it is entirely up to you. Hey everyone! Today I am very excited to bring you a special promotion from Skillshare. Skillshare is an online learning community with more than 25,000 classes, and as an Art of Engineering viewer, you get your first month completely free with unlimited access to the entire library. Millions of people are already using Skillshare to learn cutting-edge skills, network with peers, and discover new opportunities, and I highly encourage you to give it a try. With classes taught by the world's best teachers spanning categories like design, business, technology, and more, there is something for absolutely everyone to learn and enjoy. If you have an interest in engineering, then you should definitely check out the series of classes by Savary 3D, with topics ranging from electrical transformers, to diesel engines, to cooling towers. Begin your free 1-month trial today using the link in the description, and start learning with Skillshare. As always, thanks for watching, and I'll see you in the next one.